Okay, so Forge is our HPC development solution that includes our debugger, DDT, that's what we're going to be focusing on today, and our performance tools, performance reports, and map, which we covered a couple weeks ago. Tools are really focused on HPC, so they're designed from the ground up for traditional HPC workloads. So a lot of focus on multi-threading, in particular OpenMP type of threading, and multi-process programming, typically with MPI, SPMD type of applications. So that's really the sweet spot. What we're focused on is and very scalable. So both the user interface and the architecture is scalable to arbitrarily large machines. Very common in the community. I think we're on most of the top 500 machines that do HPC. We're supported on Intel, ARM, NVIDIA GPUs, and recently on ARM GPUs, not on ARM GPUs, on AMD GPUs. So once again, ease of use, especially in profiling, with our profiling tools very focused on easy to use for most users. All right, DDT, which we're going to be focusing on today. And I'll be going in and we'll be doing some demonstrations on all of these capabilities, but I'd like to highlight them in the slides. And then I think these are some of the most important features for the HPC focus. So scalable print statements, the ability to output values from the user interface without modifying the code and doing it in a very scalable way. So when you're looking at hundreds or thousands of processes that have multiple threads, very easy to sort through the output. Watch points, the ability to halt execution dependent upon the value of an expression. Static analysis. This is one of my favorites, especially when you're starting with a new code, say you're picking up somebody else's code, is we look for problems like uninitialized variables, memory leaks, things that can be caught without actually executing. So really encourage users to look for these little warning signs when you're starting out, especially with a new code. And then some of the memory debugging capabilities, being able to read or write, detect a read or write outside of a defined array, memory corruption of the stack, memory leaks, those type of issues. Performance stuff, we covered this last week, so I'm not going to say much on that. Once again, similar to last week, I'm just running within a local VM on my machine, so everything's going to be quite small scale, but the appearance and how things work is similar at 4 processes as it is at hundreds or thousands of processes. Okay, I've got a sample code that I'm going to run with 4 processes. It does not using OpenMP, so no threading. For now, I'm not going to use memory debugging. We'll get back to that later and cover that. And there's some new capabilities in that area that are fun to show also. Okay, so let's go through the user interface a little bit. At the top, operations for running processes, stepping into and out of blocks of code, manipulating the stack frame. Disassembly, somewhat new. It's been a couple of years, and this is one that I think was added while we were at ARM. And it's interesting of how I think, we've had to put aside, or been able to put aside assembly level debugging, but as we're moving to different architectures and very different types of designs, the need to look at assembly code is actually on the rise again, which kind of painful, but necessity. Left-hand side, kind of a project navigator, kind of like a typical IDE where you can search for tokens across your project, kind of navigated through a tree structure. the ability to look at various threads. So in my case, I started up with four processes, and you can hover over each block to tell what the thread is, and you can select different blocks to tell which context. So let me step along a few steps here and instantiate a few things. Okay, so on the right-hand side, we have a various view of variables. You can hover over a variable and get some information about its type and its value that's been instantiated. You can drill down into the structures. So especially for structured type elements, being able to see sub-elements, very handy navigator for looking at those. And then to the right of the variable, there's a little plot, a sparkline plot, where you can hover over that sparkline plot and get some information about the value. So for my rank, for example, we can see that we are now looking at the context for rank 2. So all the variables we are looking at are the instantiated variables for process number 2 that we've selected at the top. Or I can switch to process 0. And we see how it's updated, showing my rank of 0. And all the values are the same in this context, but in a program where processes have diverged, it's a very useful way for seeing the different contexts of different processes. And we can click on that plot. Bring it up and look at it at the sub-elements. You can actually change the value. Or compare it across all the processes. And we can see that we show some statistics for the variable across all the processes, and then see the actual value for each one. And a lot of flexibility for exporting this as a CSV file. Okay, let's step along a couple more steps. So on the main pane, source code view, as I mentioned, we had these little warning signs, so some static analysis for problems like uninitialized variables, variables that are not free, that have been allocated, those type of issues that can be statically detected. Also, we integrate with source code control versions. So for example, if you're using Git, it'll show to the left of each line some information about the provenance of that line of code, with the idea being that new problems typically occur near recently changed code. So you can see kind of the history of each line of code. The blue line, really important for when you have a lot of processes. It's a quick way to tell the location of each process. So if we hover over the line, in my case, it will show that all 4 processes that I'm running are on line 108. But in situations where things are diverged and you've halted all the processes, a really quick way to see those locations. Okay, breakpoints. Let's start with breakpoints. So I'm going to select a line that I want to halt on, go to the breakpoints tab, and then bring up the dialog. So if you right click within the body of the tab and bring up the dialog, it's really self-documenting of what can be done, how things are done. So usability wise, I really encourage in DDT, there's a lot of accelerators, but especially when you're starting, use the dialogues, and it really is kind of self-documenting of how you do things. Okay, so we can set a breakpoint for a line location or a function entry point. We can apply it for a specific process or a process group. So if we know that the problem is located in a subset of processes, really a good way to focus it. One thing we really encourage is in kind of methodology focused training is really try to apply methodology to your debugging. So, for example, giving some thought to what is the domain space of the error. So, for example, if you know that it doesn't happen until after a certain iteration, we can set that. Or typically as a conditional. I think probably one of the most common ones is you have a problem and you know it doesn't occur till after iterator ijk equals whatever. Set a conditional and focus the search, which has a lot of benefits of, most importantly, the data that you have to sort through to isolate the problem is less, and it's less overhead on the debugger. So I'm going to set my breakpoint unconditionally, line 143, all processes, not for no defined process group, and then not limiting the iterator space. So one other thing on process groups, another focus for that is it's interesting starting to see more coupled model type programs. So for example, I come from the WRF world, and there was a lot of coupled models where you might have one part of it focusing on the atmosphere, one part of it focusing on the ocean, part of it at a boundary layer, those type of designs. This is a really useful tool. Of a lot of times you're only looking at part of that model, and setting up a process group for the subset of processes that are working on that is really useful. Okay. So add a breakpoint 143 at play, and this will advance all of the processes. So we can see a dialog is halted and showing that all 4 processes are halted on line 143. So one other comment on breakpoints. One thing I encourage is always putting a breakpoint on finalize. Even if you don't think you're going to need to look at all the processes, different flavors of MPI handle that a little bit differently. And it's good to halt all the processes before they end, before they fall off. Okay, breakpoints. Let's go to watch points. So once again, use the dialog. It's kind of self-documenting. Go to the watch point tab, bring up the dialog. Somewhat similar to a breakpoint, we can set it for a specific process or process group, and then give the expression. I'm just going to give a simple expression with a variable name. We can select the watch point to halt for read or write or both. I'm going to select for read or write. You can select play. So we see all 4 processes advanced to line 149, and it will show the old value of the variable and the new value. They're really useful for cases where you get to a location in the code and the state is not as you expect, but you don't really have any a priori idea of where things went wrong. It could be way upstream, it could be in other modules, other libraries, those type of things.
Oh, may I interrupt quickly? Can
Yes.
you maybe explain the difference between breakpoints and watch points?
Yeah, that's a good question. I realize I didn't make that clear enough, and it's an important distinction. Is breakpoints are explicitly at a location. So they halt execution of one or more processes at a location, and that location can either be a line number or a function entry point. So if you give the name of a function, it will halt upon entry to that function. So breakpoints are inherently about a location. And by the way, this is a nice, we can go back and we can actually edit these, and it'll be kind of the list of the breakpoints we have. Watch points are inherently about the value of an expression. So it's independent of a location, it's tied to the value of an expression.
Thanks.
So another comment on watch points, good to bring up on this, especially since you guys are on a quote different architecture, is depending on your machine, there's a certain number of watch points that are supported in the hardware. And I believe on most ARM architecture chips, that's a relatively small number compared to on x86. And when you have a watch point that's supported in hardware, it's very minimal overhead, tends to be very quick. But if you have more watch points than you have hardware, support for. It's done in software and it can typically be really slow. So if you're using a lot of watch points, on x86, I believe it's usually the order of 6, but on ARM, I'm not sure about that. But just be kind of cognizant of how it's supported. And when you get to a certain number, it will say implemented in software. And just be wary that that will be a lot slower than if the machine is halting for you. Okay, breakpoints by location, watch points by value of expression. I'm going to show trace points, but I've kind of bypassed my favorite location to work with that. So I'm going to select restart.
May I interrupt again? Because there was just a question in the chat. I don't know if you can see the chat.
Can we write custom expressions in the dialog box, or is it intended to only work with things like variables that are already defined in the code? Oh, that's a good question, because I did a fairly simple expression. You can put any expression that's valid in the current context. So I could say being watched greater than 2, any C expression that is valid. The variables do have to be in scope, however, at the point where you define it. So if being watched had been a variable defined within a function, the watch point would only be valid at a point where the variables that I'm using in that expression are instantiated and in scope. Well, they don't have to be instantiated, they have to be in scope.
Thank you.
Yeah, thanks for the question. That's good clarification, because my example was artificially simple. Okay, so I'm going to rerun the program, and this kind of highlights another nice capability in DDT of when you're running through a real batch system. It'll take a while for your job to get submitted, depending on the nature of your machine. But once it is running, you can restart without having to go through the batch system. So I'm just going to rerun, and if I was on a batch system, I wouldn't have to do an S run again. I wouldn't have to wait in the queue again. Also, this highlights another one, in that is you can edit code directly in the editor window. So if we go to the file menu, we can tell DDT how to build our application. It's not intended to be a sophisticated building tool. It's typically just calling your script or calling a makefile. So for this case, for example, I have a simple makefile that'll rebuild my program.
Sorry, when we compile, do we need to put any specific flags to use DDT?
Yeah, in general, I recommend using -00, build with a -00 and a -G. Obviously, there's some cases where if you have a bug with optimized code, you'll need to set that. But in general, you definitely need a -G to get the symbols to be able to correlate with source code. A couple other comments on that is if you do have to turn the optimization up, try to keep it as, start with 01, 02 before going fully optimized. Another one is if the default -G tends to put a lot of symbols in. And if you have a situation where your program is using a very high percentage of the node's memory, you might have to play around with using a -G1, cut down on the number of symbols, but definitely some form of -G to get symbols to correlate source code. Okay, trace points. So I mentioned in the slides kind of the scalable print statement, I like to call it. It's called trace points in the tool. So once again, let's use the dialog to set up the trace point. Similar to a breakpoint, we can set this for a specific line location or a function entry point, specific process or process group. And then specify the variables that we want to output. In this case, I'm going to output the values of X and Y. They're just kind of loop control variables in this simple loop. Once again, give some thought to how you can focus your search. So for example, in this case, we might want to just get a high level view of what the iterator space looks like. So I can maybe say just output every other pass. Once again, conditional, really powerful for cases with like, nested cases, and it doesn't occur till IJK greater than whatever and IJK less than whatever. So a lot of capability of focusing your search. Okay. So I have a trace point on line 128. So I'm going to go to the next block past that and run all processes to line 133. Okay, so once again, the blue line shows us the location of processes, and we see that all 4 have advanced past that block that was populating the tables array. And at this point, we can go to the trace point output. So we get the output similar to a print statement, but using the sparkline plot that we use in the locals tab. Explicitly see the range of the variable and the spark line at each iteration where we halted. So my run here, obviously pretty simple. It's just 4 processes, but we can run this with hundreds of processes and it would appear very similar in this output. So a really useful tool for looking at larger scale runs versus, trying to output in a print format. Okay, so we saw the locals tab, very useful for looking at atomic variables, structured type variables. Looking at array data, it can be useful to bring it up kind of as a visualization or a spreadsheet. So let's have a look at this tables array. So we right click on the token. So another usability tip in DDT, there's a lot of functionality that's accessed through these kind of context menus, kind of a right-click context menu in this case. So when you're looking on how to do things, highlight a token, right-click on it, and it'll probably highlight some capabilities that are relevant in the context. In this case, what I want to do is I want to view that array. Right-click on the token and bring up the array viewer. So in this case, it's picked up that this was a 12 by 12 static variable. By default, I'm going to have a look at it as kind of a spreadsheet form here. We can kind of subsample the data. So especially in spreadsheet form, we could say, kind of focus in on the indices of interest, a lot of flexibility for putting in simple expressions in this only show if dialog. We can export the data. So we can save this as an HDF file or as a CSV file to look at it externally. So a lot of kind of interesting use cases. One I saw recently is some folks had a program that was behaving differently between different versions, and they wanted to look at a slice of data from a structure similar to what I have here, and they were able to output it in HDF. And this was in the NCAR community, so people use HDF a lot. Output in HDF, write a simple Python script and be able to do kind of a view of a slice of a variable across versions of a program. So a lot of flexibility that introduces by being able to output slices of your data.
Sorry, quick question. This table that you just showed, is it the same as the Y shown in the spark line that you mentioned, or is it a different table? Does it included there?
So this is multi-dimensional. The spark lines are kind of one-dimensional.
Right. So can I ask, sorry, maybe this is just a nice question again. So what is a spark line exactly?
So a spark line is essentially a 2D XY plot of the variable across processes. So the horizontal axis is the process, and the vertical axis is the variable value. So it is it is a given variable, an atomic variable plotted across
Got it.
processes, where you kind of imagine the horizontal axis as the horizontal axis of the plot.
Got it. And then the table you showed was for within a particular process, was it?
It's a yes. So at this point, when we bring up the array view, we are so tables is defined as a 12 by 12 static variable in each one of the processes. In this case, I'm looking at the value of the tables variable in process 0.
Got it. Okay. Thank you so much.
Yes, thank you. So we have it as a spreadsheet. We can also bring it up as a visualization. So with larger data sets, obviously this can be a nice way to see that the data has the a priori values that we expect, or the processing looks correct. So a larger scale, this is a very useful way to do that. Or we can sample the data set and bring it up in a spreadsheet or as a visualization, but really useful way to see, did I initialize the variable in the form that I expect it to be? After the processing, does it have the apparent shape that I expect it to be? Those type of questions as you're stepping through in the code. Also, as I recall, you guys were kind of interested in GPUs, but not doing a lot in that. Do I remember that correctly from our profiling day?
Yes, so especially on Ookami, we currently don't have any GPUs available.
Okay, so I didn't plan on spending much time talking about GPUs today, but I did want to highlight that everything that I've shown so far works and feels the same in GPU code as it does on host code. And I always am reminded of that when I get to this, because on GPU coding, there's a lot of steps where things can go wrong. You have to stage your data on the host, initialize it, get your data to the device, do your work on the device, get the data back to the host, make sure it's okay. And this tool is a great way on that workflow to see that each one of those steps is as you appear. But just also wanted to highlight breakpoints, trace points, watch points. Those all work and behave the same on GPUs as we've done today on the host. So I won't go into a demo of that, but just wanted to highlight that does work. Okay, the other one I kind of wanted to highlight. So those are kind of the basic, kind of what I view as core debugging elements: breakpoints, watch points, trace points. Some other tools for looking at the state of your programs, we'll call it parallel stack view. So this is similar to what you might get from GDB, except it integrates all of the stacks into one view. So especially as we get to larger scale where processes are diverged, really useful way to see where each process, the stack backtrace of each process. In terms of use cases, I found this is for typically communication problems. If you have a deadlock or race conditions, this is kind of my tool of choice to often be able to see the nature of problems with that, is seeing different stacks in different locations and where blocking occurs, and often be able to detect blocking and race condition type problems. So another one of the tabs, input output, pretty obvious that is. That's what you just be getting on the console if you're running directly. Logbook. So I kind of touched on methodology, and I've been trying to make this more of a focus in the last couple of years. At the last GTC, I did a presentation just focused on debugging a methodology, and with our follow-up material. I think I gave it to you after the profiling session, but it's one of the references I had in the follow-up materials. I went in depth of trying to use methodology and kind of presented that in the context of using the scientific method of make a hypothesis of what you think the problem is. What are you going to do to test it? What are going to be the parameters of your experiment, so to speak? This is all language that I think resonates in HPC, in that, software engineering HPC tends to be folks from the sciences. And so this is something that's well understood. And, it sounds a little odd at first. And I think debugging is a different discipline, in that no one sits down and says, oh, I'm going to spend a few days or a few weeks trying to find this bug. Just the nature of it is we want to think that we're going to have a quick look at it and find the problem. And that's often the case, which is great. But for the situations where you get hours and days and weeks into the problem, if you start from the beginning every time, being methodical about how you're approaching it, I think it could be a lot more fruitful. So the logbook is a tool to support that, but whatever approach works for you, the important thing is to keep track of your experiments. What's the nature of the bug? What are you going to test to find out if it's wrong? And keep track of that. And the logbook gives you a way to do it of making some comments, keeping track of the state. See the state of the program as you're stepping through. Let me just step a couple more steps. And when Rudy goes through offline mode, you'll see in offline mode, it has a very similar look and feel to this, stored into an output HTML or CSV file. It's a really useful way to log your experiment. So if you get to the end and you didn't find the problem, you can save it off as an HTML file. So if it does become one of those bugs that go on for days or weeks, when you get a week down the road and you say, boy, I tried something really similar to this a few days ago, what was the parameters of that experiment and what was the outcome and what did I try? I think you'll find it's very fruitful for those type of problems that become really challenging. So logbook, evaluate windows. So the evaluate window allows you to actually change the state. So the locals tab, I kind of view it as the static view of variables. You can drag a variable to the evaluate window and actually modify it in quite a few ways. So for example, you can change casting type. So especially on different types of integers, of shortening or widening types in integers, playing with the floating point type of casting. And probably one that's most common is actually just directly editing the value. So for example, you'd say, boy, I'm at this position. If the variable equal something different than what it currently equals, that would probably be the correct state. So once again, make a note in your logbook of like, I'm changing the value because I believe this is my hypothesis. And then run your experiment. So my rank is a pretty easy one to see. So I'm going to try that. So let's say I'm going to change the actual value of my rank for process one. So for example, at this point, I'm able to look at the value of a variable in all of the different processes. And for this test, I'm going to change it for process one. All right, so we see the spark line updated. You see the outlier. I mean, typically my rank should range from like 0 to n-1 and be kind of a monotonically increasing simple curve. And we can bring up the cross comparison view and see the actual outlier in it. So this highlights another aspect about these spark lines. So one thing that comes up is obviously in this case, we only have, I don't know, 16 pixels to work with, or something of that order. They're not a lot. So when you're running at hundreds or even dozens of processes, there's not even enough pixels to represent every process. When we're running a large scale, we do kind of a statistical smoothing of this, if you will. So if there's outliers, it'll jump out as it does in this case. So even for this simple code, if I ran it at 100 processes, there's not enough pixels to represent that, but I would still see this single process outlier. So the intent is, it's not going to show you the specific problems. It's going to highlight that you have a problem. So the kind of workflow, if this were running at larger scale, would be to bring up the actual comparison. Okay, so that's kind of what I view as the core debugging features. And memory debugging is definitely an important part. In fact, I kind of encourage folks to use, when you're in development mode, to always turn on memory debugging. And there's a lot of capability there. But I think, as I mentioned, what I'd like to do is pass it over to Rudy for a little while to talk about offline debugging, which out exaggeration is probably one of my favorite features. A lot of really difficult problems kind of grand challenge debugging problems have been found with offline debugging. So I really like to highlight. So I'm going to let Rudy go through that, and then after Rudy, we'll come back and talk mainly about memory debugging.
Cool, thanks, Bo. Do you want to just unshare your screen, then I can share mine?
Yeah, I think we're there. Can you share now?
Just give me a sec. Just one, yeah. Is it busy sharing? There we go. Okay, desktop one. So can you see my screen okay now?
Yeah, we got it.
Yeah, sorry, I'm on the Mac, and my Mac gets a bit silly sometimes with the permissions, but seem to be able to get there.
No, looking good. We see it all. Yep.
Okay, so if we just look at offline debugging, so just start with the documentation. So this is a good place to start, especially if you want to look at any features of Forge. So if you go into here, you can look at DDT, and it's quite easy to find the offline debugging over there. Yeah, so if you want to use offline debugging, you usually start your application and you just run this -- offline to run it in offline mode. So the good thing about offline mode is if you don't like using a GUI, or you don't want to click through buttons, you can just run everything offline, and DDT provides a report for you at the end of it. And the important thing to note is when you're running this offline report, you can either spec -- output equals the name of the file. But if you specify that, you have to put HTML, otherwise it defaults as a plain text. And if you don't specify this, then DDT will just provide you some random file name for that. So here's a couple of examples there, but I can run through this using my. So can you see my command console?
Yes, but could you make it a little bit bigger, the font? Because it's a bit hard to read. Perfect, thank you.
Yeah, so better.
Yeah.
Okay, so I'm on one of our internal machines, and what we can do is we can run this application. So maybe let's just run it without the tools. So I'm running MPI exec and with 4 processes, and I'm running wave C for say 5 seconds. So this will just run this application, and you might just want to say, okay, well, if I want to look at some of these variables, and then what you can do is you run the same MPI exec application, but you run DDT and you set it in offline mode, and then I'm specifying this HTML file, which I wanted to be called when I run that. So if I run that, it's going to run for 10 seconds, but that should be enough time. So this kind of removes the whole need for the UI. And as you can see, this application is run, and it should create this debug log at the end. Yep, and it's called the one that I name it. So as I said, this is on one of our internal machines. So what I need to do is I need to copy that across to my local machine. So if I SCP, so Mars, and then there's HTML log onto my local machine. And what I can do is I can open this with Firefox. Offline debug with HTML. Yeah, so what you can see is this is a very basic log. So currently all it's busy saying is what application we ran, and it gives you some metadata. We ran wave C for 10 seconds using MPI exec with 4 processes. So there's nothing very interesting that it's busy saying here, but if you look at these documentation, what we can do is we can manipulate the offline debugger to give us a little bit more useful information. So things we can do is we could do mem debug to provide some memory debugging. And we can also do a snapshot interval. So if you think we're currently just running for a few seconds, but if your application is running for a few hours, we can say get a snapshot every couple of minutes, and you can specify how many minutes you want to get that snapshot. And then the ones that I'm going to show off today is when you specify trace point, you provide this syntax, and this syntax is exactly the same as what we see in the GUI. So, you know, when you have the GUI, you can see stop after or start beginning after the nth visit, and trigger for P amount of times. You can also specify conditions. So this is give exactly what you can do in the GUI, just represented in a command line option kind of a way. So the best thing to do is if I show this off with an example, and what I can do is go back to my source code. So we should probably start off what this application actually looks like. So this is a demo code, and what we can see here is this J variable, it just increments over time. And what we can do is we can set a breakpoint over here to kind of test out this debugging, and we can test out what this variable J is giving us back over time. So this is line 216, and what I can do is if I do break at. So again, we're doing the exact same commands, but instead we're doing break at, and we're giving wave C 216 to put a breakpoint at the line number we just said. And as the documentation says, this variable here or this line here says that we don't want to stop after a specific amount of times this breakpoint is hit. We want to just hit it every single time. But every 100th time this breakpoint gets hit, we want to log the stack view as well as what this breakpoint is telling us 100 times. Actually, so we only want to do this breakpoint. We don't want to do the evaluate at this point. Okay, so if I run that, and you can see that this will run a little bit slower because we're actually setting some breakpoints on the application. And as it is busy running, breakpoints can be quite expensive. So you don't want to be running, you know, thousands of times and collecting all the logs 1,000 times from the actual application. So you want to be quite sparing with when you're setting breakpoints and what you're getting back from the application, because it does add some overhead, which we can see here. And before it was returning, but this maybe takes an extra 2 or 3 seconds because of the amount of breakpoints that we set. Again, we can take this offline log back, but I've cheated a bit, and I've already got this on my system. So offline debugging. And so what this is giving us now is extra information. So this is giving us all the stacks and some of this variable. So we set this breakpoint at this line here at wave C 216, and we can see all the variables. So I is 0 and J equals 1. So this is the very first time the breakpoint gets hit. But we set it so we want to evaluate this every 100 times that this breakpoint is hit. So the second time it runs, so the second time the program counter went into this line of code over 101 times, and we can see the value is J, and this should increment continuously 301, etc., all the way to 901. So what you can see here is it's just giving us the the variables every time the breakpoint gets hit, and we can manipulate how many times we want to set this breakpoint over the execution of the program. Do you have any questions, or should I carry on?
Maybe I just have a very general question, because I never saw this offline debugging before, but I think it's really cool. Can you tell us some examples where users would rather use offline debugging other than using the GUI?
So one thing I could see is if you constantly changing your code, and you might want to debug this as you're going along. So you know that a particular variable should always be this value. And what you can do is you can change your code and then continuously run this, and you continuously check that value and say, okay, I've not broken my code yet. So it kind of works as a bit of a validation suite for as you're developing your code. And you can put this into job schedulers as well, and maybe put something in there to automatically check that value. So as you run it, it automatically validates for you.
That
I
makes
think even like I mentioned, some of the some of the best success stories, so to speak, we've had is with this capability. I think two of the big ones that those are usually connected with are super big scale. So for example, NCSA had a problem where the code only had an issue when it was running full scale. Obviously that's really hard to do interactively with the GUI for a lot of reasons. Whereas in offline mode, they set it up to run on the next reboot and found the problem on the first try. So I think super large scale is one. Another one that I think is getting more successful is where you have something that's non-deterministic that takes hours before the problem comes up, is you can put in a ton of instrumentation in offline mode. You can just gather a ton more information than you could reasonably do with the user interface, and then post-process that information. Those are the two cases where I've seen customers have really challenging problems and have success when doing it in offline mode instead of with the user interface.
Yeah, that makes sense. Thanks.
Cool. Yeah, I'm just a bit conscious of time, so I'm going to wrap this up a little bit. So the extra commands that I put on here, because you can extend these commands out as you like. You can put breakpoints, trace points, etc. But what I've done here is I've just put some evaluate commands in as well. So what I'm doing is I want to evaluate J every time this breakpoint is hit, and also want to just put in sort of a custom evaluation. So I'm doing J multiplied by J multiplied by 3. And what this is kind of showing is that you can do your own calculations every time a breakpoint is hit, and then depending on what that returns, you can kind of say, is this something I expect, etc. So if I go onto here, and again, I've already taken this off the machine a while ago, but I can evaluate this command. And exactly this is showing what we saw again, all the breakpoints, breakpoint I, etc. But the extra information that we put onto this log is this evaluate. So we're evaluating J here. You see what is the value of J when this breakpoint is hit, and also our custom calculation there as well. And we can also look at the current stacks, etc. Okay, yeah, so that's everything from here. I could show memory debugging as well. So you can do that in here, and if you put the right debug commands on the command console, you also get some debug information. But as Bo's going to show us how to do that in the GUI, I kind of recommend just trying that if you've got some time with the offline debugger. Okay, yeah, that's everything from me. I'll just hand back over to Bo.
So Rudy, there's a question in the chat. Can you see that, or do you want me to read it?
Yes, sorry, I've got it up here as well. One sec. I'm not too sure, to be honest. I don't know if you can answer that, Bo.
So you can in a couple ways of, so you can save this output in a CSV file instead of an HTML file and make that part of your regression testing. So you would have kind of script it up of, if you have CSV file of run n and run n-1, You can script it to look for doing that differencing that you want to. We also integrate the output with some of these toolkits like a Bamboo and Jenkins, where it can automate some of that. To tell you the truth, my experience has been, I'm kind of old school about it, but the easiest is just create a CSV file and create the scripting in your regression testing that would do that differencing.
I guess like the question is like, scripting makes complete sense. Like the question really is like, could we make the pipeline automated, for example?
Within DDT to have the knowledge across runs?
Yeah, I mean, either exactly. Yeah, within or maybe there's like a super process that controls both DDT and the sort of offline analysis. Do you know what I mean?
I think so. So,
Yeah.
So let me explain a little more of like another context for that is, so as I mentioned, Rudy showed the HTML output, which I think is great for that type of thing when you're like looking at larger amounts of data, sometimes saving it as CSV, and that's pretty straightforward. It's in the documentation, is doing kind of a parameter sweep where you can script a lot of differences where you submit your job to run DDT many, many times with different parameters on the command line as Rudy illustrated. And then your scripting would look at the difference. We don't have within the tool to know, like you can't run DDT and have it have knowledge about a previous session inherently. You can look in the scripts.
Just to clarify, I didn't mean previous session. I think what I mean is like within the same session, but let's say going from like one iteration to the next, right? Could we specify like a threshold and says, okay, flag me when it's like a big difference? And it comes up quite often in, let's say, like an ML pipeline or when you're trying to like sort of reduce a loss function, for example, right? So that's why I was asking.
So with it, using the evaluates option that Rudy illustrated, I think what you're talking about might be possible, if I understand, is if you have a variable that's defined, if you've defined epsilon in the code and it's in scope at the point that you want to do that difference, I think you could do it in that way. The challenge with that is if you have variables in the code that are not used by the code itself, the optimizer will usually eliminate them. And so you have to do some trickery to get around that.
Got it. Okay. Appreciate it. Thanks.
Well, thanks, Rudy. That was really just an introduction. As I said, this I think is one of our most powerful and one of my favorite success features. I forget even, did I share with you last time kind of some follow-up blogs and webinar stuff? I think I did. I'll do it again in case we didn't. So there's a ton of capability around the offline mode. And I have a couple blogs that kind of go into a little more simplification than we have in our documentation. But yeah, this is, I think, is a great feature. Okay, so I will pick it up with memory debugging. All right, you got my screen again?
Yes.
Okay. Okay, so memory debugging covers a pretty broad swath of memory-related problems that we look into. Things like reading or writing outside of a defined array, heap corruption, tracking of memory allocations and memory freeing. So let me start with the simplest, just kind of just reading outside of an array. Okay, so we need to turn it on. Typically by default, memory debugging is off. And there's historical reasons, but as I mentioned, I really encourage folks of when you're in development mode, making lots of changes, rerunning your job, is just run within the debugger IDE with memory debugging turned on. And this is kind of the kind of a default that I recommend. And just subjectively watching over time, these are a set of flags that impose pretty small overhead on your run. So balanced, and this just enables a bunch of flags for heap related problems. Guard pages, this is what's probably most relevant in this example, which will detect if you read or write outside of an array. Very low overhead, so pretty much always want to turn that on. Then some additional features related to kind of dynamic memory. Once again, this is just kind of a subjective recommendation of what catches a lot of problems with relatively low overhead. Now, depending on the type of code you have, like you have really modern, rich C++, it's doing a lot of memory activity, a lot of runtime instantiation you might want to tweak with this. Once again, been focusing in your search, so if you can limit this to a subset of processes, it's going to reduce the overhead from the debugger. It's going to reduce the overhead that you are looking at. And in all fairness, for a lot of SPMD codes, especially when you're first looking for memory problems, you can probably find the problem by looking at just a small subset of the entire process space. So a good way to focus your search. Okay. So once again, just 4 processes in my local node here. Another one I'd like to mention, so there's 2 other debugging tools that I'm a big fan of, is Valgrind. Does a really thorough job of looking for memory related issues, but it is extremely high overhead. So for a lot of those type of problems, I recommend at least starting with the debugger, and I think you have a very high chance you'll find in the debugger, but Valgrind is a great tool. I definitely support that, but the overhead is enormous, especially if you're running a lot of processes. So I recommend starting the debugger for that. Another one that I think is a great tool for this exact problem where you read or write outside of a defined array is the Intel compiler in particular has flags that will build in checking to detect that. But once again, a lot of overhead. So if you're a fan of that, for kind of, I'd recommend just starting with the debugger with the guard pages capability turned on. All right. So we got some Fortran just to mix it up for fun. Once again, I'm going to select play to run all processes. Oh. So this was feature that I was going to show next, but it looks like I had it set wrong. So capability we introduced in a somewhat recent version is you can say halt processes when you reach a certain threshold of memory on the node, and it looks like I have that turned on with a low threshold here, so I've hit it. So and it's locked up. VM locked up.
In that case, it looks like
What's that, Rudy?
sorry, you had a bit of an echo. Can you just go on? Can you just go on mute? Yeah, I was just going to. It doesn't matter. Sorry, there's just a bit of an echo. Oh, it's gone. Yeah, I was just going to say that error message seemed like it was reasonable because you said a memory threshold and the debugger was actually hitting that memory threshold, which is good. But I think you said your VM just got locked up.
So yeah, if you can give me a minute to restart the VM, it locked up. Yeah, that did happen, Rui. The mistake I made was I didn't mean to have the memory threshold turned on. I had it turned on at a super low number. So it hit it before overrunning the race. So let me restart my VM. It's going to take a second. All right, I think I'm back. Are you getting my screen again?
Yes.
Yeah, set memory threshold. So I set it for really low value. So I'm going to unset that for now. I've got another example that shows how to use that to detect memory leaks. This program really doesn't have a memory leak. So it was exhausting memory too soon. I think I made a mistake of asking the new company for a Windows machine instead of one of those fancy Apple machines, and I got the weakest Windows machine that Dell will sell us. So it can be a little slow starting up. Okay. All right, so we have memory debugging turned on. Particular guard pages is the feature for detecting reading and writing out of arrays. And there we go. So at this point, so it's saying that we are reading or writing outside of an allocation. And this variable RES is a static allocation, and we've attempted to read at a bound address outside of it. So as I mentioned, good way of detecting that type of capability, similar to compiler flags that will build in the checking board, but a lot less overhead. Okay, so given I've kind of already talked about the quote new threshold capability, I'm going to move on to an example to kind of explicitly illustrate that. So this was I think it's actually been out about a year, but we didn't advertise it so great in the previous release. So I really like to highlight this, and then I think it's a great tool for detecting memory leaks. This is another one we've already had success stories with. I think it was in CESM, which is pretty mature, long-standing code at NCAR, had a situation where certain configurations would have a memory leak problem, and this capability helped find it. Okay, once again, the setting of interest is set node memory threshold. And I'm just going to put a really low percent so we hit it relatively quickly. And what this will do is when that percentage of the node's memory is exhausted, it will halt the processes. So play all. And so it halts on, it halted on line 60 here. When I get rid of the dialogue, we'll be able to look at that better, but it's showing that we have hit that threshold. And pretty obvious in my case here, I just have an infinite loop that's attempting to allocate memory. So I think this is a really great addition to DDT for memory leak exhaustion type problems. One that's come up since it's been out also that I think is interesting is the situation where you want to tweak your code to use an extremely high percentage of the node's memory, get the most efficiency and typically the best throughput is for a certain configuration. You might want to tweak it to very high level memory. Our performance tools, especially performance reports, can help with that. But I think this feature is actually a way to do it in that you can set a threshold at a level and kind of iterate through finding what that boundary is. So another way for kind of optimizing the maximum amount of memory on a node. Okay, one more kind of a approach or set of tools for looking at memory. Memory usage and memory stats. So let me, there we go. So once again, kind of the defaults here, balance, guard pages. Won't be using it in this run, but it's very low overhead. So I leave that on. Don't want to look for exhaustion in this run, checking heat consistency. Okay. So what I'm going to do in this case is this program is doing a bunch of different allocations and has something of a memory leak type of problem or misallocation problem, shall we say. So I want to just essentially run to finalization. So I'm going to have a breakpoint on finalize, no other watch points. Play all processes to MPI finalize on line 234. So at this point, there's two tools of choice for looking at memory usage. There's memory stats, memory usage under the tools menu. So tools, memory stats, memory usage. I like to start with memory stats for a couple reasons. It gives kind of a higher level view of what's going on, showing the allocations by call count, by byte count. So we can see right away here, the process 0 has some anomaly going on about the memory that it's allocating. That may or may not be a problem, but very quickly we can see that by quantities. Another reason stats is to kind of like start with this is this information is cached in the main DDT daemon on the login nodes. And it does not have to go out to the compute nodes to gather the information. When we go to get detailed information on the nodes, it'll have to go out and get some information on that. So I just wanted to have we talked about this a little bit in the performance engineering day, but just a reiteration on the architecture in DDT and MAP. So it uses the same architecture where when we start up, we create a daemon on each one of the compute nodes that manages the processes on that compute node. And it sets up a tree hierarchy where each compute node communicates to a set of parents, and those parents communicate up the tree. And depending on the nature of your network and the size and that type of thing, the tree will vary in shape. But conceptually, it's setting up a tree that enables logarithmic communication of commands and data. And this is particularly important in DDT relative to MAP, in that things like when you hit a breakpoint, that breakpoint has to be communicated to each one of the processes. And that communication occurs through this tree architecture. And so even at very large scale, it's very responsive because the size of the response is logarithmic through this tree architecture. Also with data, so for example, when you go into the array viewer and you need to bring back a slice of data from a specific process or a set of processes, that data are communicated up this tree at a logarithmic fashion. So that's kind of the heart of the scalability in our design in terms of communicating commands and data through this tree architecture. So kind of relevance here. So we start with memory stats and then memory usage. Now at this point, it will actually go out to each one of the processes and gather that. So you can see in my case here, I only have 4 processes running on one node, and it gave me a little progress dialog. So at very large scale, going out to gather that data can take a little bit of time, but aggregating that for a large run across all the processes is going to be at least logarithmic in the scaling of it. Okay, so now we're getting a little more detail. So for each one of the processes, we get this bar chart where we can see to the right has legend what it is. So for my case, that big chunk seems to be in this allocate member function in packet. Then there's a few smaller ones. And we can play with like how many we want to look at a time. In my case, it looks like, everything except the allocate member function looks like system related stuff. So we probably don't want to care about that too much. See the allocation histories. So then the kind of the workflow with this tool is click on a part of the bar chart. So click on that big chunk in process 0. And then in the details, it'll give us the actual addresses and quantities of these allocations. So they all look like they were the same quantities, but we get a pretty long list of allocations. And from here, we can navigate to the source code by clicking on that and bringing up a dialog that will actually show us the stack history to that allocate member function. And then by clicking on that, actually go to the source code where the allocations are occurring. So another approach for memory related problems, this is unlike the threshold variable, this is also useful for just studying the nature of allocations to see that not only leaks, but the kind of methodology or kind of nature of how you're doing allocations is as you expect. So memory stats, memory usage, threshold capability for seeing leaks, all great ways for looking for leak methods, proper memory allocations. One I want to just mention again, and I think I talked about it in our performance day, is another tool which is actually gaining preference. I'm finding it for large codes, especially if you don't know the code. I mean, a lot of times I'm helping folks with codes where I don't really know the code, is the memory profiling in MAP, is using the profiler to find the locations in source code where memory is making jumps or expanding at a rate that you don't expect. I think we went over a brief illustration of that. So when looking for those, this is a case where I really encourage both the tools within DDT and the memory profiling in MAP. Just checking my notes here. So I think that's the bulk of what we had to cover. As I said, on offline debugging, I really encourage you to have another look at that. There's just so much capability around that, and Rudy covered really the core part of it. But if that's a capability that's new to you, and it's kind of a different paradigm in debugging, is creating debug output without an interface. I thought it was a little novel when I first looked at it, but it's a really powerful capability. So I really encourage more in-depth of that, especially when you get to having some of the type problems I mentioned that are large scale, non-deterministic oriented. So we have any questions? I think that about covered it. I guess, I take it back. I did one more other one. I know we touched on it. As I recall, Python was something you guys kind of used, but is not mainstream. Do I recall that correctly?
Yes, we have quite a few Python users. Not the majority, but we have quite a few. Okay, let me just give a super quick illustration of Python. Now I want to reiterate our Python support. So we support Python in DDT and also in MAP and performance reports. In fact, the latest release of our tools has a lot of additions for supporting Python
in all of our tools at this point. Most everything you would want to do in debugging is supported with Python, profiling supported Python. So a lot of new Python stuff in the new release, but we really have focused on what is kind of our core sweet spot, as I mentioned, is HPC codes. So codes that are typically SPMD, things that are often using MPI for Pi. That's the sweet spot of what we're trying to support. That said, we're definitely working to better support ML workloads. The most recent release of performance reports, I think, does a great job of that. It highlights how time is being spent in communication and IO, which is often where multi-node training problems might go awry. In DDT, it pretty much works. I think in terms of ML workloads, it's not like we need to debug into PyTorch or TensorFlow. Those are obviously pretty reliable. We don't need to profile into those, but seeing at a high level that things work. So let me just give a simple illustration of how to run it with Python. It's a little quirky. It's a little bit different than so this is just a super simple Python code. It's no MPI or anything, but the main quirk with DDT and running Python is how you start it up is a little bit different. So here we go. Simple Python code.
I really like the code.
We just need to increase 9 to a bigger number. That's all. Okay. So we have to specifically specify the Python that we want to use, and then this flag. So a couple comments on it. So once you know that this is how you have to do with Python, it's pretty straightforward. We do have it on the wish list to make the starting of Python codes, especially when MPI for Pi is involved, a little simpler, but it turns out that's not a trivial task. And like when it comes full circle, do we want to make this look cleaner, or do we want to add more functionality, making those tough types of decisions? We've been going with the latter. So yes, it's a little quirky, but once you know how to do it, it's pretty straightforward. So I got something wrong in the ordering. So that looks right. As I recall, last time we met, I was still using our previous version of the program, but I got brave and updated after that. The downside of that is when you're working with a new release, I tend to be pretty fortunate of finding issues. So Rudy, you have any ideas of what went wrong there?
Okay, just look at the command line again quickly. Yeah, you have the ordering wrong. It's a linear _ Python _ debug. So it's not a linear debug Python, it's a linear Python debug. Yeah, that should do it.
All right, so it's ran every process, and we see the reframe and the output here. He set a breakpoint. So I just kind of want to highlight that most everything kind of looks and feels as it does with compiled codes. All right, so we're getting the navigator, the source code. Hopefully you have a view of locals. So yeah, so we're getting the locals view. And so this is a single process, but one of the additions in the new in this release, the new release is having the spark mines and the ability to look at structures. So I think pretty most all of the things that we went over in the core demo are now working with Python. A few pieces offline debugging is not yet, but that is coming soon. But most of the interactive things are straightforward. Oh, so yeah, any questions?